As I described briefly before, the file system is the part of the operating system which allows processes to use the storage devices in the system. In one sense, it's just the set of system calls which allow those interactions. The file system is typically a bit more than this though, because it imposes a basic structure on the data. So when a process uses the file system, it doesn't see the storage devices as just big buckets of bits. First off, the storage areas of the storage devices are split into what are called partitions. A partition is basically just a contiguous chunk of the storage space. Quite often, the whole storage area of a storage device is made into just one big partition. So, for example, here in the diagram we have a hard drive, and the whole storage area of that hard drive is made into just one big partition, partition 4. Similarly, the flash drive just has one partition which takes up its whole storage area, partition 5. The other hard drive though, and the CD-ROM drive here, have been split into multiple partitions. Also notice on these drives, we've left some space blank. Those spaces don't belong to any partition, and so effectively they're really just not seen by the file system, and they're effectively just going to waste. It's inside partitions where we store files. A file simply is a logically contiguous sequence of bytes. And by logically contiguous, I mean that the bytes are not necessarily stored contiguously within the partition, but as far as the programs reading and writing these files, the bytes of the file appear to be in a set order, and each byte one after the other. So right there, one abstraction which the file system provides for programs is each program doesn't have to actually concern itself with how the data is actually getting stored on the device. In any case, within a partition, each file must have a unique identifier number. So here the partition has 4 files, file 35, 3, 7, and 61. Each file's ID within the partition has to be unique. We can have on some other partition, say, a file with the ID 7, but because it's in a different partition, it's distinguishable between file 7 in this partition. Do note that the diagram here seems to be implying that files are always stored contiguously within the partition, but as I discussed previously, that's just not the case. So say file 7 here might actually be spread throughout the surface of the partition. In addition to files, partitions also contain what are called directories. Like files, directories also must have unique identifier numbers, but a directory is always a listing of names and the file number or directory number associated with each one of those names. So in directory 21 there might be an entry for the name foo, which is mapped to the file ID 35, and the same directory might have an entry named bar, which is mapped to directory 86. A key limitation with directories is that they can only list files and directories which are in the same partition. As long as the file or directory is in the same partition though, it's fair game. In fact, somewhat surprisingly, a file or directory can be listed in multiple directories on the same partition, and in fact it doesn't have to have the same name in any of those directories. Also somewhat surprising, a directory can even list itself. Now, within a partition you always have at least one directory, and this is the special directory called the root directory. The root directories are special because they are given special names, and those names are ultimately what we use to refer to any file or directory by name. In the case of Windows, each partition is given what's called a drive letter, a unique letter that identifies that partition, and usually this letter is followed by a colon. So say in our system we have 3 partitions, and the first partition is mapped to C, the second is mapped to H, and the third is mapped to D. Well then, if I want to refer to the root directory of partition 1, I refer to it as C:/. The root directory of partition 2 is H:/, and the root directory of partition 3 is D:/. These are what are called file paths. A file path is simply a string of text which designates the name of a file or directory. If I have the file path C:/Adam/Nixon, well, that refers to the file or directory named Nixon, which is inside the directory named Adams, which is inside the root directory of the partition mapped to drive letter C, in this case partition 1. H:/Taylor/Polk/Hayes refers to the directory or file named Hayes, as listed in the directory named Polk, as listed in the directory named Taylor, as listed in the root directory of the partition designated H. Lastly, d:/Garfield refers to the file or directory named Garfield as listed in the root directory of the partition designated D. In Unix systems, rather than giving partitions drive letters, we instead first select one partition which we want to mount at what's called root, the root of the whole system. The root directory is designated as simply /, so here partition 2 is mounted at root, and so the root directory of partition 2 becomes the root directory of the whole system, of the whole file system. To get the other partitions into the picture, we mount them into directories of some partition which is already mounted. So here, for example, if we mount partition 1 at /banana, that means within partition 2 we're creating a special directory named banana, but that directory isn't really a directory on partition 2, it actually is just a pointer to the root directory on partition 1. So the file path /banana ostensibly refers to a directory listed within the root directory of partition 2, but in fact it's treated in a special way such that it actually refers to the root directory of partition 1. Similarly, if we mount partition 3 to /lemon/apple, then the system creates within the root directory of partition 2 a directory named lemon, within which it creates another directory named apple, and that directory apple is treated in a special way such that it actually refers to the root directory of partition 3. So, given these mountings, when the file system sees a file path of /banana/adams/nixon, it goes to look in the root directory, the root directory of partition 2, for a directory named banana. It sees that that directory actually corresponds to the root directory of partition 1, and so it goes and looks there for a directory named Adams, and within that directory it looks for either a file or directory listed as Nixon. When the file system sees the path /Taylor/Polk/Hayes, well, again, it looks in the root of the whole system, which is the root of partition 2. It looks there for the directory Taylor, in which it looks for the directory named Polk, in which it looks for the file or directory named Hayes. And finally, when the file system reads the path /lemon/apple/Garfield, it first again looks in the root directory of partition 2, it looks for a directory named lemon, within which it looks for a directory named apple, and it finds it and it sees that it corresponds actually to the root directory of partition 3, so it goes and looks in partition 3 for a file or directory listed as Garfield. So that's all we'll say about files for now. We'll get into the details of reading and writing files in a later unit, because that's the sort of thing which varies quite a bit on different operating systems. The last thing we'll briefly mention in this unit is what's called IPC, short for Inter-Process Communication. IPC refers generally to any kind of mechanism provided by the system that allows processes to talk to each other. One obvious mechanism for IPC is simply to use files. If one process writes a file and then another process reads it, well, that's communication between processes. Using files, however, isn't always an appropriate mechanism, mainly because of performance considerations, and so systems generally provide several other mechanisms for IPC. Namely, on Unix, for instance, you have what are called pipes, and then you also have what are called sockets and signals, and also you can have what is called shared memory, which is really exactly what it sounds like. You can have two processes which get the same chunk of RAM mapped into their address space, such that any changes made to the memory area by one process are seen by the other. That and the other IPC mechanisms are things we'll get into in later units. I just mention it now so that you don't get the wrong idea that processes are always totally isolated from each other.